This is Food Science 571, Food Process Engineering Technology. This is Dr. Barrett Vaughn of the Department of Food and Nutritional Sciences. This is Topic 2, Physical Properties, and we are concluding our lectures in this series with a special section on texture. Texture of food materials. Sensory manifestation of the structure of food and the manner in which this reacts to applied forces. The specific senses involved being vision, kinesthetics, and hearing. Also, all the mechanical, geometrical, and surface attributes of a food product perceptible by means of mechanical, tactile, and where appropriate, visual and auditory receptors. Textural properties are a group of physical characteristics that arise from the structural elements of the food, are sensed primarily by the feeling of a touch, are related to the deformation, disintegration, and flow of the food under a force, and are measured objectively by functions of mass, time, and distance. These are definitions of texture of food materials. Also related to the texture of food materials is the relationship between the texture and the viscosity. Texture is important to the overall acceptability of most foods. This goes into food preparation, processing, and consumption, and also into HACCP, which is Hazardous Area Critical Control Points. You have measurement of texture of food materials, which is sensory as well as objective or instrumental. With the instrumental, you have different types of instrument that measure texture, and what they measure may be the stress, the tensile strength, compression stress, shear stress, torsional stress, strain, modulus of elasticity, Poisson's ratio, tensile strength, bow yield point, plasticity, and viscoelasticity. It could also be measurements of compression, puncture, bending, compression, extrusion, torsion, and tensile, and also TPA. Here is a diagram showing the differences in texture. What you're seeing is a scanning electron micrograph of the fractured surface of a hydrated lima bean seed. The left-hand side is uncooked. The starch grains can be seen inside the broken cells. On the right-hand side is how it looks after it's been boiled for 20 minutes, and the cell walls do not break. The starch granules can be seen pressing against the unbroken flexible cell walls. From your own experience, you know that there is a difference between an uncooked bean and a cooked bean in terms of the texture of when you actually bite in it or press on it. And this can actually be seen from this scanning electron micrograph, how the internal structure of it, the texture of it, is actually different. This is a table that shows changes in food texture during storage. What you will find is that the texture changes during storage for most foods depending on the way that it's been preserved or packaged. You see that at the top you see bread where the texture changes, in terms of the crumb itself. The firmness increases, the springiness decreases, and the cause is starch retrogradation, moisture transfer from the starch to the gluten. For foods such as eggs, you see fresh eggs, you see that the viscosity of the eggs decreases. And the reason is that you have the loss of CO2 through the shell changes the protein. For things such as ice cream, coarseness increases, butteriness, sandiness, and crumbliness. And it's because the ice crystals enlarge, the clumping of flat globules give you the butteriness, the crystallization of lactose produces sandiness, and poor protein hydration produces crumbliness. Other examples are shown on this slide, showing the changes for meat that's frozen. You have freezer burn and drip, where what has happened is surface desiccation and reduced water holding capacity. Also, something like pickles, you have a softening where the degradative enzymes, exogenous or microbial, actually cause that softening. For example, when you have fresh vegetables, you may have a toughening, a softening, a pitting, or a loss of crispiness over time, and that really also depends on the type of changes in texture that are going on due to chemical changes within that particular food. This is a table of textures of wheat and wheat-based foods, ranging from wheat grains, breads, cakes, donuts, shredded wheat. And what you see is that you have a particular percentage of water that ranges from as low as 4% in, say, a cookie to as high a percent as 80%, which you would find in a hot breakfast cereal. And there's different forms which produce different types of textures. For example, your wheat grain, which is an elliptical solid form, you have a very hard and vitreous texture. However, for a cookie, which is the form as a disc, some are hard, crunchy, and crumbly, others are soft and chewy depending on the formulation. Also, for something like a flour, which is the form as a powder, it's not consumed in this form. However, a pie crust, which has a lower water percentage, is given in sheet, is tender and dry. So depending on the form, the shape, how it's been treated, as well as the water content, you'll get different textures. And most of these textures are specific to the particular food, and some textures are more desirable than others. When it comes to texture measurement, it can be fundamental, empirical, or imitative test. Fundamental tests measure well-defined rheological properties. The property measured may not be related to sensory attributes, however. The strength of the material versus chewing into smaller pieces, and assuming a small strain, which can be 1 to 3%. You also assume that the material is homogeneous, isotropic, uniform, and regular shape. Normally, biological materials are none of these, and it really uses expensive equipment, but you have to do a correlation with the sensory problem, which really ends up being slow. Another technique really are empirical techniques where you're measuring parameters that are poorly defined, such as textural quality. They're rapid, easy, and inexpensive to measure, and there's an arbitrariness of the test which becomes product specific. You also have imitative tests as well. When we speak of the fundamental tests of texture, we have to understand some of the principles. These are examples of torsion, compression, bending, and torsion loading that you might put a food under, really to measure the types of properties that go into the texture. When we look at the stress-strain relationships for metal, curvilinear, and bioyield materials, you see that soft food and bioyield materials exhibit very different stress-strain relationships than you would have for metals. In testing these material and mechanical properties, there may also be some specialized types of equipment that are used. For example, in this slide, you see a hamburger patty tension tester, and you also see a shearing device that has fixed plates for a round sample, which is the Warner-Brachler shearing device. Another set of specialized equipment that may be used for testing food material properties are the Kramer shear press, where you see the blades and a top grid placed on a plate on a box, and also you see a 3-point bending test fixture, which is shown on the right of this diagram. Here we see examples of compression tools with spherical ends. And you see you have a parallel plate contact, a single plate contact, a spherical indenter on a curved surface, and a spherical indenter on a flat surface. And what these will do is give you different measures of the properties of the food, and which one really depends on what kind of vegetable that you're really dealing with in what state. For example, each of these different contacts can be used on either a whole vegetable, a vegetable cut in half, a fruit cut in half, or a slice of fruit. And what you are actually measuring depends on how the different material properties would be in that particular form of the food. This is another diagram that gives you more background on material properties testing. This is a schematic diagram of the two compressions required for the texture profile analysis test. The first diagram shows the downstroke actions during the first and second bites, and B shows the upstroke action during the first and second bites. And with this type of fundamental testing with equipment, you'll be able to find certain properties that you're looking for in the material. It may seem that some of these texture measurement tests are rather abstract, but here are some examples of applications of texture measurement tests. The first type of test, when we talk about compression tests, it could be for the firmness of bakery products, the firmness of fruits and vegetables, which would be important in terms of freshness, in terms of quality. Tensile testing could be the adhesion of a food to a surface, which could be a pizza topping, gluten, a packaging material, those kinds of things that would be important in terms of food quality and quality control. In terms of bending, we can look at the texture of breadsticks, the freshness of vegetables, for example, a carrot or celery, and also chocolate bars and biscuits in terms of quality control. When we think about puncture types of tests, we think of the skin stress of fruits, which may be such as tomatoes or other kinds of fruits that puncture would be an issue in terms of quality. When we talk about puncture and penetration, it could be the firmness and hardness of gels, yogurts, butter, margarine, and fruit, things that are processed that you would need to be sure that they have a consistent quality. And also when we talk about extrusion, that could be toothpaste or particulate products. This diagram shows a generalized texture profile analysis curve obtained from the Instron Universal Testing Machine. In the table below, we consider the dimensional analysis of TPA parameters, and we have mechanical parameters, the measured variable, and the dimensions of those measured variables. You have hardness, which you actually measure the force. When you have cohesiveness, you measure the ratio that you see in the last diagram. Springiness, you measure the distance from the last test. Adhesiveness, the measured variable is the work. The fracturability or brittleness is measured from the force. The chewiness is work. The gumminess is force. And so using a test like we saw on the last slide, you're able to find out certain parameters of the food itself that can be measured from that test. This concludes the special section on texture of physical properties, lecture 4 of 4. If you have any questions, please feel free to contact me at the email address given in the syllabus. Thank you.